Okay. The last speaker of the day is Mareike Wolff from Kiel University. And she is going to talk about Newton maps with Julia set of Lebec measure 0. And I think that you can share the screen.
Yes. Yes, you can see it?
Yes.
Yeah, great. Okay, yeah, I will talk about Julia sets of Lebec measure 0. I would like to start with some general results and then afterwards talk about an application to Newton's method. Yeah, okay, we will talk about meromorphic functions, in particular transcendental meromorphic functions, and they are interested in the Julia set. And we denote the set of singular values of f's by S of f, so the set of critical and asymptotic values and the limit points. And then the post-singular set of f is defined as the closure of the forward orbits of the singular values. Yes, and I would like to talk about some general theorems about Julia sets of Lebec measure 0. And the assumptions for such theorems typically fall into two categories. One is that the post-singular set is in some sense nice, and the other one is that the density of the Julia set in certain subsets of the complex plane is not too large. And in order to make the latter precise, we need the following definition. We take a measurable subset A of C, and then A is called thin at infinity. Basically, if the density of A in any sufficiently large disk is bounded above by some constant strictly less than 1, and where by density we mean the, the measure of A intersected with the disk divided by the measure of the disk. And we call A thin at a point in C if the density of A in any sufficiently small disk which has that node as a boundary point, and such a disk is bounded above by some constant strictly less than 1. And we call A uniformly thin as a subset of C if, well, it is thin at every point of B, and the maximal size of the disk under consideration and the upper bound for the density of A in this disk do not depend on the particular point. Yes, now we have the necessary terminology to actually state some results. The first one I would like to mention is by McMullen, who proved that if f is an entire function and whose post-singular set is a compact subset of a Fatou set, and whose Julia set is thin at infinity, then the Lebec measure of the Julia set is 0. For example, this can be applied for to the function lambda times e to the z for lambda between 0 and 1 over e. And then I would like to mention some generalizations of these results. And all these generalizations assume that the Julia set is thin at infinity, but impose weaker assumptions on the singularities. And the first one is by Stella to show that it suffices to assume that the distance of the post-singular set to the Julia set is positive, but post-singular set does not necessarily need to be compact, so it may be unbounded. And where this has been further generalized by Jankowski and Zhang, who, first they both allowed F to be meromorphic, and they also allowed for certain exceptions to the condition that the distance of the post-singular set to the Julia set is positive. And the one by Zhang, which is more general than the one by Jankowski, more precisely says that if F is meromorphic, there are at most finitely many post-singular values in the Julia set, and the set of post-singular values which lie outside of some large disk has positive distance to the Julia set, that then if the Julia set is thin at infinity, its Lebec measure is 0. Yes, and my goal now was to generalize this and to actually, under some assumptions, allow for an unbounded sequence of post-singular values whose distance to the Julia set tends to 0. But before I state this result, I would like to talk about some limitations. The first concerns the condition that the Julia set is thin at infinity. This cannot be left out in general. For example, if we consider the function sine of lambda z for modulus of lambda less than 1, one can easily see that the post-singular set is a compact subset of the Fatou set, but McMahon showed that the Lebec measure of the Julia set is positive. And so it doesn't suffice to assume that the Julia set is thin at infinity. There are functions whose Julia set is thin at infinity and there's positive measure. For example, where Biff and Chirita have shown that there are polynomials whose Julia set is positive measure, and for polynomials the Julia set is always bounded, so in particular it's thin at infinity. But one can also construct transcendental functions whose Julia set is thin at infinity but has positive measure, for example, by approximation theory. Okay, so much about what cannot be done. Now it's turn to think that actually can be done. So we suppose that F is meromorphic, and then we suppose that there is a compact subset P1 of the post-singular set, which will serve as some sort of exceptional set, such that P1 has finite intersection with the Julia set. And then we suppose that the Julia set is thin at infinity and uniformly thin at the post-singular set minus P1. And under these assumptions, we can show that the Lebec measure of the Julia set is 0. Okay, let me give an idea of the proof. The very rough idea is to show that, that up to a set which is obviously small, the Julia set contains no points of Lebec density of itself, where a point of Lebec density essentially means that the limit, where that if we take the density of the set in some disk and let the radius of this disk tends to 0, the point of Lebec density would mean that this is equal to 1. Well, and the Lebec density theorem says that if a set has positive measure, then almost every point of the set is a point of Lebec density of the set. So if we can show that outside of the set of measure 0, we don't have density point, then the set must have Lebec measure 0. And well, how do we do this? Well, essentially the first step is that the Julia set is uniformly thin at the post-singular set minus the set P1, which has finite intersection with the Julia set. This first yields that the intersection of the post-singular set with the Julia set has Lebec measure 0. And then if we take some point which is in the Julia set, but not in the post-singular set, or in fact never mapped to the post-singular set, and then we will relate the Julia set near Z with the Julia set near iterates of Z. We iterate this point Z under some suitable subsequence. Just map to Fn1 of Z, say. Then we take some disk around Fn1 of Z, which does not intersect the post-singular set. And then we show that the density of the Julia set is bounded above by some constant strictly less than 1, which does not depend on the particular iterate. And well, how do we do this? If we can take the disk to be very large, then we use that the Julia set is thin at infinity. If there is, the disk has to be small not to intersect the post-singular set, and we have a point which is in the post-singular set but not in P1 and lies at the boundary of this disk, well, then we use that the Julia set is uniformly thin at the post-singular set minus P1, and we can also deal with the points being in boundary points in P1. And then, well, since the disk does not contain any points from the post-singular set, there is a holomorphic branch of the inverse of Fn1, which maps this disk back to some neighborhood of Z. And one can show that also this condition that the density of the Julia set is bounded above by some constant strictly less than 1 then carries over to this neighborhood of Z. Well, then we can further iterate, do this again, get another neighborhood of Z, and using the blow-up property of points in the Julia set, we can show that the size of these disks around Z must shrink to 0, and this implies that Z is not a point of Lebec density of the Julia set. Yes, and all together, where we can show that, like, let's say most points of the Julia set are not points of the Lebec density, and then the Lebec density theorem yields the desired conclusion. Okay, so much about the proof here, and now let's turn to an application to Newton's method for a certain class of entire functions. We consider the function g of z equals some integral from 0 to z of some polynomial times e to some polynomial plus constant. And then Newton's method for g consists of iterating the function z minus g over g prime. And in general, Newton's method for entire functions has the property that the zeros of g are attracting fixed points of f, and the simple zeros are super attracting fixed points. And the critical points of f are the super attracting fixed points of f and the zeros of g2 prime, which are not zeros of g or g prime. And well, for our function g under consideration here, G2 prime is some polynomial times e to the q, so it has only finitely many zeros. So all but finitely many critical points or critical values of f will be super attracting fixed points. And also one can show that for our function g, the function f does not have asymptotic values in C, so each singular value must in fact be a critical value. Okay, and then we want to show that under certain assumptions the Lebesgue measure of the Julia set of f is 0. We suppose that g is not just some polynomial times e to some polynomial. This corresponds to the fact that f, the function from Newton's method, is transcendental. And then we denote by z1 up to zn the zeros of g2 prime, which are not zeros of g or g prime. So the critical values of f which are not super attracting fixed points. And then we suppose that fn of zj is attracted by a periodic cycle for all j. That is, there is some periodic cycle such that the distance of fn of zj to the cycle tends to 0 as n tends to infinity. And then we can show that the Lebesgue measure of the Julia set is 0. And this theorem is related with the theorem by Walter Bergweiler, who showed that if for the same function, if fn of zj converges to a finite limit for each j, then fn of z converges to zeros of g everywhere in the Fatou set. And under the assumption that fn of zj converges to a finite limit, it is not difficult to see that this limit must be a fixed point of f, and that's a 0 of g. So the theorem essentially says that if fn of zj converges to zeros of g for each j, then this convergence actually must hold in the entire Fatou set. Well, and a fixed point is a periodic cycle of period 1. So under the assumptions of theorem 3, also those of theorem 2 are satisfied. And combining these theorems, we get that if n of z converges to zeros of g almost everywhere in the complex plane. Okay, and an analog of theorem 2 was that the Lebesgue measure of the Julia set is 0 under these assumptions. For functions of which are some rational function times e to the az plus some constant. This is essentially due to Jankowski. Well, if R is a polynomial, these functions also belong to the class of functions from the previous slide. But more important than if we consider rational functions or integrals here is that where Jankowski considered only polynomials of degree 1 in the exponent, and we allow for arbitrary degree. Okay, then I would like to give some example. For example, the assumptions of corollary 1 are satisfied if g of z is integral of e to the minus t squared dt plus constant between minus square root pi over 2 and square root pi over 2, or for g of z equals z squared plus 1 times e to the minus z squared plus c for c between minus 1 and 0, so that Newton's method for these functions converges to zeros of g almost everywhere in C. And for both functions, there are also parameters C such that f has a cycle of period 2 in the Fatou set, and such that the zeros of G2 prime are attracted by such a cycle, so that the assumptions of theorem 2 are satisfied, so that the Julia set has Lebec measure 0, but there is a subset of the Fatou set where the iterates of F do not tend to zeros of G. Okay, so much about examples. Now I would say a little bit about the proof of theorem 2, where the idea is to use theorem 1, which was this general theorem about Julia sets of Lebec measure 0, and whereas exceptional set P1, we take the intersection of the post-singular set with some large disk, and well, by our assumptions on the zeros of G2 prime, we can arrange it. Well, first, the assumptions imply that the intersection of the post-singular set with the Julia set is finite, and we can take R so large that each post-singular value outside of this disk is a super attracting fixed point of the function f. And yeah, then we have to show that the Julia set is thin at infinity and uniformly thin at the post-singular set minus P1. And this is done by showing that the attractive basins of the super attracting fixed points have a certain size and are sufficiently close to each other. Are sufficiently close to each other, and that the Julia set must be thin at infinity and uniformly thin at the super attracting fixed points. But doing this, well, okay, we still have some time, but if I would explain this in detail, this would still be too much for the time of the talk. So let me stop here and thank you for your attention.